So, as many of you will know, since at least not the age of 19, since I started studying at the University of Utrecht, University College Utrecht, I was studying humanities at that university. I was studying philosophy, politics, literature, and history, in addition to political science for my minor and required course in biology that I also took. However, in my spare time, I was studying theoretical physics and cosmology and astrophysics and these sorts of subjects pretty obsessively on the internet. And I was building up a great deal of knowledge, and I never really slowed down in the pursuit of that endeavour. I don't know when exactly I set my sights on trying to understand gravity. However, I eventually left that university for all sorts of reasons, mostly to do with mental health. Learned a great deal while I was there, got okay-ish grades, I think. A smattering of A's, B's and C's like I usually do, due to, frankly, preoccupation with things like writing books in my spare time, work on a novel in my spare time, learning physics in my spare time, and like paying more or less lip service to the curriculum. And that's like really why I got B's at school and things, because I was deep diving constantly on the internet when I was at school about things like peak oil and alternative energy and all sorts of things I was really interested in and wanting to learn about, and paying lip service to education and not focusing on my schoolwork so much. But I mean, yeah, I didn't exactly fail school. I did okay, but I mean, I was a lazy student. I wasn't actually lazy. I was constantly learning, at home and at school. But that's beside the point. So anyway, a few years later, after I left University College Utrecht at the age of about 23 or so, I was helping my grandmother move house in France by doing a bit of painting and tidying up around the place and just generally getting the house ready to be sold and all this sort of thing. And I've been studying physics in my spare time still, just like, as often as I could in my spare time. And I was reading through an A-level physics textbook that I'd illegally downloaded just to try and familiarise myself with some more rudimentary concepts before trying to approach the bigger, more nuanced, more complex topics in physics. And I was trying to understand quantum mechanics at the time. So one of the things that they were talking about in the quantum mechanics sections of that textbook was electron volume probability densities, and this sort of cloud of electrons that we find around atoms, basically. So if you look at very often we look at gold atoms underneath electron microscopes, and these atoms they exhibit a cloud, sort of a fuzzy. They look like fuzzy little balls under an electron microscope, and the fuzziness that we see is light basically bouncing off the electrons surrounding the atomic nucleus. And this tells us a lot about quantum mechanics. So I thought in terms of how an atom would generate a gravitational force, my basic idea was that the electron is almost always within the sphere of high probability density around an atom. It's within this area that's roughly defined by the van der Waals radius or the Bohr radius, possibly for a hydrogen atom in its ground state. And I suspected that the electron might be able to jump just a bit further than that and possibly appear near the nucleus, near the protons in another atom. And given that an electron has a negative charge and that protons have a positive charge, I suspected that a particle exchange could happen between these two particles of differing charge, and that a force of attraction could exist between them, and hence we get gravity. We get an attractive force operating over a distance. So I worked with this idea for many, many years. I'm 33 now, so I've been, I suppose, working on this for 10 years or so, and it has thrown up a great deal of possibilities, I think. It has integrated very nicely with general relativity, I would have said. I would have said that you could recover all the central predictions of general relativity using the fundamental assumption that a gravitational field is an extension of the electron volume probability density of the atoms composing an object. So it also explains nicely the behaviour of light, so far as it pertains to light travelling around objects. And it's thrown up a great deal of problems over the years and things I've had to solve, and there's been objections to it, as there always are with any kind of new physics. And it sits very nicely also with theories in the legacy of physics, theories which were once very widely accepted. And I'm talking about things like the ether here, and ideas that we might get from de Duillet or Lesage, these sort of forgotten physicists of the past who were once very prominent men in their field, and who were proposing a kind of a particulate basis to the gravitational force, which indeed ether theories also sort of do. And we might also think that, you know, explaining things such as Newton's third law, for example, this idea that we have to lose mass in order to go faster. That's more or less how that works. So, we chuck propellant out of the back of a spacecraft when we're in space via Newton's third law, that the object is losing mass. But also what it's doing is that propellant is pushing against something in the background. And this creates a very nice, I think, intuitive picture of the gravitational force. I think this it allows us to arrive at Newton's third law, and it allows us to derive it, let's say, from first principles and work backwards to the same conclusion that Newton found, if you see what I mean. What I wanted to really talk about in this video, however, was the caveats to this, what we might need to dispense with in physics, that we have this thing called the Standard Model, this periodic table of the elementary particles, of these two basic classes of matter and antimatter, and then within the fundamental particles we have the bosons and the fermions, these particles of half-integer spin and integer spin, i.e. fermions and bosons respectively, and we have also these antimatter particles, which was an assumption made by Paul Dirac, and I don't want to... The angle I was going for with this was that antimatter doesn't exist, but it's a phantasm. It's at least improperly named, and that's what I said in the short video that I recently published to YouTube, but my opinion might be somewhat drifting from that, really right at this moment, and perhaps the positron is just merely a new particle of matter that gets absorbed by background electrons rather than strictly annihilating, if you see what I mean. And we need to reappraise antimatter, I think, because we've got this big outstanding problem in cosmology called the baryon asymmetry problem. This problem of why the universe seemed to create so much more matter than antimatter, or like why all the original matter and antimatter annihilated, leaving only matter left behind, because it has the flavour of something a little bit arbitrary, does it not? Something a little bit cobbled together and seemingly superfluous almost. And whatever you think about a model of the universe and a model for fundamental physics, I would submit that it should never contain anything that is superfluous. I think everything should have some sort of function. I do not believe we should multiply entities beyond necessity. I think it should ultimately be elegant. It should involve the minimum number of particles necessary to explain physical phenomena that we observe. So, building on this, where do we go from here? I would submit that antimatter is not necessarily a unique phenomenon. After all, if we could create antimatter, why, via some equivalent process, can we not also create matter? The rules for matter seem to be quite clear. Matter can be neither created nor destroyed. That law of the universe seems to hold up to our best experimental test of that basic principle. That seems to be something that seems to be a hard and fast law of the universe. We cannot create matter, We have never created a quark or an electron or anything like this. However, we have indeed created positrons. So, like, what I think about positrons, what I was going for initially was that the positron is some sort of manifestation of the W plus particle. This heavy boson, which is 150,000 times heavier than the electron, a truly large, massive particle. What I would like to say about that is that I might still agree with that position, and that what we're really observing when we're observing positrons is a W plus particle taken out of an experimental setting, for one thing. Say we're observing a positron travelling through the universe, we need to be cognizant of what it's travelling through, what its medium is. So let's say these background electrons exist for a moment. We have an alternative explanation for the Higgs mechanism, or we're going to put an alternative spin on the Higgs mechanism, and removing also the Higgs boson as a unique fundamental particle, which I believe it isn't. I don't believe it exists. I don't think the Higgs boson is a real thing. I don't think we ever directly detected the Higgs. What we have detected is its decay products, and I think it was a naked singularity produced in a Large Hadron Collider, and I think that it may decay into gamma rays, possibly. It may decay into a few other different things. However, I believe it still was the result of the collapse between two colliding protons into a very brief singularity for a minute fraction of a second before decaying again into more recognizable particles of matter. So, is it a W plus particle, a positron, for example? I believe it could be, perhaps, because the mass of the W plus is probably determined by the extent to which it interacts with its background. And positrons will eventually annihilate via an electron, though I wouldn't have said annihilate so much as I'd have said perhaps absorbed by an electron. And in exchange for the positron, which is swallowed by the electron, as soon as the electron swallows it, it tunnels to somewhere else in the universe, and something happens, and energy is emitted, probably gamma rays from the annihilation of the positron, but the positron really is a W plus, and what we've got going on in the universe is a universe in which these background electrons are constantly tunneling between different locations in the universe via the laws of quantum mechanics. Say a photon hits an electron, the electron swallows the photon, it absorbs the photon. That process of absorption collapses the electron's wave function, in essence measuring, right, the position of the electron. So what do we have to consider in quantum mechanics when that happens? That the momentum of the electron becomes uncertain, becomes unknown, and indeed unknowable, probably, I've said. So we massively increase the certainty with which we know the electron's position, briefly. What occurs next is faster than light travel. So, is it travelling infinitely fast? Is it merely travelling faster than light? We know that tunneling electrons travel faster than light. They do not travel at light speed between different locations. They travel instantaneously. So, we know this from quantum theory. Integrating that into general relativity, what we have to build up is a picture of clouds of electrons surrounding massive objects, all of which are constantly tunneling between different locations. An electron leaves one location, a new electron shows up in its place. The configuration space in which it's showing up has shifted, and since the classical object to which it's bound is moving in space, so we've got a minute void which exists very, very briefly for an electron from somewhere else in the universe tunnels to its location, and that's as a consequence of this second quantum revolution that we've undergone. this revolution of non-local realism, that this idea that any given electron in the universe, at any given time, well, is a single electron, but taken over a long period of time, there's no reason why it need be locally real, why it need be the same electron each time. It is a different electron each time from somewhere else in the universe. And they're tunneling perhaps once every unit of the Planck time. Photons are actually moving faster than light between different points on the background. It may well be a different photon each time, since it's absorbed, it's kicked out by an electron appearing, absorbed by another one, that disappears, electron replaces it, emits a photon, photon comes out faster than light, some speed faster than light, that's all I know about that. Absorbed by an electron again, electron disappears, new electron takes its place, new photon, and so on, and that's how we get the wave characteristics of a photon, and it moves classically through space at light speed in a vacuum. So, going back to mass generation and antimatter, what I believe probably about that is that we can get a W particle moving through space, and then this, like say in beta decay, for example, this decays into a positron, is an electron and an electron antineutrino. So it diverges into three different particles. The positron being the positive element of this, it may liberate merely an electron from the background due to its large, the forces it's generating, and the large amount of energy that it's causing to excite an electron in the background. Electron just diverges away from it, and the neutrino accounts for some small mass component of that. I'm not so certain how well we've tested beta decay, or if that is indeed just theoretical, and that we've actually detected electron antineutrinos coming out of the decay of a neutron in beta decay, the decay of a neutron into a proton mediated by a W plus particle. However, what we can say about the positron is that is the sheared off positive mass element of the W plus particle, behaving as a new particle, behaving as something with half integer spin and a positive charge instead of integer spin and a positive charge. I also came up with this fundamental, this is Lagrangian really, of how fundamentally electrons interact with protons, and I invented this model whereby it was the simultaneous exchange of a W plus particle from the proton for a W minus particle from the electron, and that these particles, in the process of being exchanged, the W plus and the W minus attract one another, and via this mass generation mechanism that has more to do with charges than the accumulation of background Higgs particles, what I would have said about that is that the positive charge and the negative charge balance out and cancel out the masses of those two particles, leaving massless spin 1 particles in what would be a massless spin 2 gauge field, which is what's ultimately predicted for the graviton, the so-called particle for gravity. And we say in theoretical physics that the force between an electron and a proton is mediated by photons. However, in this scenario, we've got a W plus and a W minus of equal mass and equal charge attracting one another mutually, and their masses cancel to nothing. Then you're left with something which is indistinguishable from a photon, are you not? So, in essence, what you've created are photons. They are the same thing, basically. They have all the same properties as photons. They start out as W particles, however. So, what's going on with the standard model, I believe, is all this sort of shape-shifting of particles and it's deeply mysterious stuff. But the more you look at it, the more I think it becomes unavoidable to think this way about matter and energy, and about this energy economy of the universe, this economy of energy whereby you've got fermions exchanging particles constantly exchanging bosons constantly with one another. So the fermions make up the particles of matter, the bosons make up the particles of energy, and your particles of matter constantly exchanging energy between one another. And that's the most reasonable, I think, way in which we can think about fundamental physics. And if I've done anything new in physics at all, it's probably saying this sort of thing, which, you know, it's new ideas, it might be treated with hostility by the community. You know, a lot of physicists will say, oh, that's ridiculous, that's bosh, you know, that's just out there woo-woo nonsense. But I wouldn't be so certain. I would think that, you know, this does push things a little bit more forward. And I'll eventually level an attack on the gluon, because I don't think colour charge exists. I don't believe in it, not really. I think the background forces of nature contribute to the cohesion of atomic nuclei, and indeed the cohesion of hadrons in the nucleus. So, for instance, I think the background electrons contribute somewhat to the stability of neutrons in the nucleus, and indeed the positive charge of the protons contributes to this also. And it might not be so simple, really, in nuclear physics as having protons and neutrons in the nucleus. It might just be a sort of mishmash of quarks, really. You know, and we can sort of say a bit arbitrarily, I think, that protons and neutrons exist. Irrespective of whatever we say about that, you know, we always say that the nucleus is positively charged, which indeed it always is. And I think that the gluon, since when it comes down to it, apart from this colour charge stuff, this Murray-Gell-Mann quantum chromodynamics jazz, what I think about this is that, I think that it's photons trapped in the nucleus, trying to force the nucleus apart, giving it a level of excitation, causing it to oscillate, more like, and less to do with the noble eightfold way of colour charge, if you see what I mean. Very beautiful model though it is, to a certain sort of sensibility, but I think it's a load of bloody rubbish. I'm sorry, I do. I agree with Feynman on that. I think Feynman actually had the same opinion as on this that I would have, like looking at that. But that's, you know, maybe beside the point. So that's what I want to say. I think we need to reappraise antimatter, probably as shape-shifting entities associated with bosonic matter, giving the appearance of being a positively charged counterpart to the electron, but really it's just a doubly plus particle, but whose mass has been adumbrated to some extent, shortened, attenuated via its interactions with particles in the background, and it will eventually annihilate. You know, well, not annihilate, but be absorbed and be carried off to some other part of the universe by these background electrons, which are matter particles, and constantly tumbling and forming gravitational fields. So I think I'll leave it at that, 25 minutes or 24 minutes or so, and I think I understand gravity. I think via this work, I said in another video that this was all a bit pointless since like so many people come up with basically the same idea. I don't think anyone actually has come up with exactly the same ideas as me though. That it's not so accurately and precisely correct as what I've come up with. That I might just pat myself on the back a bit. Having thought about this a little bit harder than many people, and perhaps introduced new and useful ideas in theoretical physics. And that's what I hope I have done. So thank you everyone for watching. I'll see you soon with yet more awesome content, and